All right. So I'm Eve Lee, and I'm an associate professor at UC San Diego. And I'll talk about the small planet population in particular, focusing on the inner regions of the planetary systems. And when we take a look at these small planets, there are multiple edges that appear in sort of multiple axes of the properties of these planets. So I'll first go through some of those before I dive into the theories and physics that we can use to understand how those edges come about. When we take a look at the orbital period distribution, there is a certain shape. So if you just plot this in scatter plot, it's a bit hard to see like what are the relevant abundances of these planets, or the occurrence rate, or the number of planets per star, depending on how you count. And especially if you correct for the detection biases, this is how they look. And this is pretty uniform no matter what kind of the types of the stars you're looking at as well. So because there are multiple screens, I'm going to use this. So in general, focusing on planets that are less than 4 Earth radii, so these are sub-Neptunes, it looks quite flat in log orbital period, but only down to at around 10 days of orbital period. And inside of that, it just continues to go down, going all the way to inside of a day. And where exactly this knee happens at around 10 days, again, this is quite uniform across F, G, K, and M, at least down to early M type of stars. Now, when we take a look at the mass period space, focusing on what people call the rocky planets, so planets that are less than 1.8 Earth radii or so, there is some sort of an upper limit at around 10 Earth masses, and this has been, like, you can take a look at this in NASA Exoplanet Archive, which is what you're looking at right now. The black points are the ones with the actual mass measurements and precise enough mass measurements. The magenta in the background are the ones that do not have mass measurements. So those are there just to give you an idea of like how many more planets you should probably target to get their masses. But this 10 Earth mass limit has been seen in other catalog as well, which is a bit more uniform catalog by our European colleagues. It's called Planet S catalog, and they also report this maximum limit at around 10 Earth masses. And that is seen across a relatively wide range of the orbital periods as well as the stellar masses, but there is some hints that like we might see something else as we go down to cooler and cooler stars. Now, in radius period space, there are multiple edges that appear. The most famous one that most people like to talk about is the radius gap. It's a bit hard to see here. On the left, what you're seeing is the raw data, so no correction for detection biases. On the right is the same plot, but now corrected for the detection biases. And there is a clear gap that is separating the sub-Neptunes from the rocky super-Earths. Now, for the purpose of this discussion, I'm going to go with the premise that most of the sub-Neptunes are the hydrogen-helium dominated envelope, but keep in mind that there are also other hypotheses saying that maybe a lot of these are also water world. But there are some evidence that might go against that, which is interesting, that I'm happy to talk about during Q&A. But again, for the talk itself, I'll again focus on the premise that they are mostly dominated by the hydrogen-helium envelope on top. Okay, so in terms of what exactly creates this radius gap, with that premise, there's a bit of a nature versus nurture in terms of when exactly it appears. So I'm going to briefly go through how we can understand this. And what I think is going on is that you can get this separation, this bifurcation primordially, like from formation itself. But of course, for the planets that are particularly close to the stars, they are susceptible to irradiation, and that can cause a further mass losses and stripping of the gaseous envelope, and that can cause a transformation of the sub-Neptunes into rocky objects and cause further separation itself. So with that in mind, what I'm going to show you is that It's basically a question of like what kind of population you should take a look when you're trying to probe the different kinds of physics. So if you're interested in the initial conditions and the formation physics, you're going to have a much better chance when you take a look at planets that are farther away from the star so that you're less susceptible to that post-formation processes by interaction with the host star. But as you go closer and closer towards the star, you're probing different kinds of physics where you're now looking at the different ways in which the stars and planets interact with themselves and the planets get further processed. So then, in terms of this initial bifurcation, what exactly is the criteria so that certain kinds of planets would just be born rocky? So this is a very classical, it comes from a very classic paper in theoretical astrophysics, and it stays true to this day. It illustrates the growth, the mass growth of a planet. This line over here in particular is the gas mass on top of a rocky core, and there's this initial slow growth, which happens due to thermodynamics. So the underlying physics here is thermodynamics. And what do I mean by that? So imagine that through all sorts of coagulation processes that I think people have been talking about thus far in this meeting, let's just say that all happened somehow, and then you have a rock. And the rock is massive enough so that we can define the heliosphere that is larger than the physical radius of the rock, which allows for this planet to build this gaseous atmosphere. So that accretion process of the gas, however, that is basically a release of potential energy, which means that there's going to be a heating. The gas heats up so that you're going to have a temperature gradient, hotter closer to the core and colder farther out. And nature really does not like having any sort of gradient. So when you have non-zero temperature gradient, nature is going to try to erase away that gradient by cooling off this gas layer. And the gas layer that is cooling off is going to shrink. So that allows for more gas to refill the heliosphere, and that is the basis of how the planet builds its gaseous atmosphere over time. Now, when you do the actual calculation and solve the full structure equations for a planet that is embedded within the protoplanetary disk in the gaseous nebula, then you're going to find the final envelope mass fraction that is a very strong function of core masses. And the different colored curves here correspond to the different epochs in the disk lifetime, so going later and later in time, going from blue to orange to green. So this line over here, that corresponds to the cooling that I just heuristically described. And in terms of what's going on down here, what's going on down there is these cores are so light that they quickly reach a maximal state where you just get rid of the entire temperature gradient. And remember, the cooling process happens because there is non-zero temperature gradient. So you get rid of the temperature gradient, you're going to stop cooling. And if you stop cooling, you're going to stop gas accretion. So this isothermal gas layer will give you the maximum mass a given core can accrete. And that is exponentially sensitive to the core mass, which is why you have this very steep drop-off. And with this very steep drop-off, this will naturally give you that separation of the planets with thick enough a gaseous atmosphere to those that is practically barely rocky objects. So in terms of how to map this into the planets that we can observe, these that lie in the still cooling regime, that corresponds to the sub-Neptunes. And that sharp fall off will manifest in terms of the relative deficit of the planets. That will give us the gap. And once the envelope mass fraction falls below around 10 to negative 4, 10 to negative 5, that's such a light atmosphere that the radius of the planet will be pretty much just governed by the central rock itself. So where does this transition happen? So that transition happens, if you just read off this plot, it happens at around 1 to 2 Earth masses. So the actual value depends weakly on the orbital period because it depends on the how hot the disk is, and it does get hotter closer to the star. But it is going to be around 1 to 2 Earth masses where we currently detect most of these planets. Okay, so that is the initial condition. Now, for the planets that are close enough to the star, so by close enough, these are orbital periods less than around 50 days or so, they're going to be subjected to a high enough energetic irradiation from the star, irradiation flux from the star. So then the next question to ask is, okay, so within those regions, within those close enough regime, then what kind of planets do we expect to be transformed as rocky bodies? And I really like this plot. This is from James Owen and Yanxun Wu in 2017. I think this illustrates really well the underlying physics behind why is it that you have this separation, that further bifurcation between the rocky versus gaseous sub-Neptunes under photoevaporative physics. The equation on the right gives a general idea of how you can calculate the typical time over which you will completely get rid of the gaseous atmosphere. So it's basically given by how much, some fraction of the XUV flux, that the radiation energy that gets deposited into the upper atmosphere against the gravitational potential of the planet itself. And that's what you see in terms of this colored curves. And for the planets whose typical mass loss timescale is longer than the characteristic timescale over which the stellar XUV luminosity stays relatively high, then we expect those planets to retain its gaseous atmospheres. So I'll go through this a bit. So why exactly is it that we have this non-monotonic behavior, some sort of a peak in terms of the mass loss timescale? So that happens because if you focus on the regime where you have very low level of envelope mass fraction, again, at that point, the radius is no longer given by the atmosphere, it's given by the core. So you're just going to have smaller and smaller total mass. So with weaker potential, it's much easier to just get rid of all these atmospheres. But on the other extreme, where you have a pretty thick gaseous atmosphere, but your total mass is not quite large enough so that you're not dealing with gas giants, then you have quite puffy atmosphere, so you present a larger cross-sectional area, so the amount of irradiation energy that the planet receives is just higher. So so that leads to, again, a very short mass loss timescale. So that's why there's a bit of a sweet spot, which corresponds to the envelope mass fraction at around the % or so. Now, the exact amplitude of these curves will go up for higher mass cores and also farther away from the star. So this is not a static picture. This does change depending on the properties of the planets. And furthermore, some cautions to keep in mind. So there's this eta factor that is the efficiency factor, like how much of that irradiation flux actually gets used to get rid of these atmospheres. It is quite a complicated function in terms of planetary potential and XUV flux, so you do need to consider that if you would like to get a precise value. Another thing to keep in mind is the XUV luminosity. It varies with time, and it is not quite certain how exactly it varies with time, but depending on what kind of stars you're looking at. So using 100 million years as the typical timescale of the high activity period, it's probably pretty good for the X-ray, as it decays pretty rapidly after 100 million years. The picture is is less certain for UV, so EUV and NFUV, because they can linger a bit longer, and it can, so much so that if you just calculate the total integrated amount of mass loss that happened after 100 million years, it's about the same as the mass loss that happened prior to 100 million years. So you do have to be a bit careful about what exactly is going on with the high energy part of the stellar spectrum over time for the particular target star you're looking at. Okay, but in general, what this corresponds to is that, So what this corresponds to is that for around 4 Earth mass objects, if you have initial envelope mass fraction of around 1%, then those are likely to survive as sub-Neptunes. And anything, and if you fall below that, significantly fall below that, then they will just proceed to being transformed as rocky bodies. Again, with the exact value that depends on the mass of the core and the orbital period. All right. So coming back to this edges in the radius period space, looking at this gap, this bifurcation, we will start with the natural bifurcation between the rocky bodies and the gaseous, the more gaseous sub-Neptunes, and that's going to happen at around 1 to 2 Earth masses. And after the disk gas goes away and the planet is just laid bare to the stellar radiation, close to the star, sorry, I should have had a less than 1% there. So close to the star, around 4 Earth mass cores with something that is less than 1% envelope mass fraction, we expect them to transform into bare rocky objects. So there's going to be a further transformation and processing. Okay, so now, not sure if you can really see it. I hope you can see it. So over here, there is this protrusion of a population for planets with periods less than about a day. These are the ultra-short period planets. And we can already see that these are not coming purely from evaporation, because if that were the case, the upper edge, I hope you can see the upper edge, because I'm not just drawing this, this really does follow the edge. This edge, it is not continuation of the evaporation gap, it falls down. So that tells you that there is something else other than evaporation that is sculpting these ultra-short period planet population. So what is going on? And I'd like to first talk about the creation of this USPs. Where are they coming from? So let's try to connect this to the disk properties, which I believe has been discussed quite a bit, probably on Monday. So let's say you, again, like you were able to create all this planetary mass objects, and if you consider like what is the maximum range, the maximum spatial range these planets could be, then it goes all the way to the inner edges of the gas disk. And where's that inner edge of the gas disk? Well, it's probably going to start at around magnetospheric truncation, which we often think is quite close to the core-rotation radius, which I believe Zhao have shown. It's not quite the same, but quite close. So if that's the case, then we can use the measurements of the spin periods of young stars to get an idea of like what that inner edge of this gas disk may be. And if you take a look at that distribution, it's a scatter plot, but if you just draw a histogram, it does peak at around 10 days, but it's not a sharp peak. There's quite a broad distribution, and it does follow along down to around a day of the spin period. It is a relatively broad distribution. So back in 2017, we did a very simple calculation where we just distributed the planets following, according to their orbital dynamical stability, and distributed them all the way down to the inner edges of the gas disk, drawing from the measured spin periods of the young stars, and we have something that looks like this, which does agree quite well with the data. Doesn't go all the way in. But since then, there has been quite a few updates in the observations. So if you make all these updates to the exoplanet data and also the spin periods measurements of the young stars, this is what we get. Again, in terms of the general shape, at least down to a day or so, it does a pretty good job at reproducing the data, but we seem to have a bit of an overabundance of these USPs. So we need to get rid of this and pull it down to the observed rate. And the short answer is we can do it if you allow for tidal decay, so tidal orbital decay of these planets. And to make it a bit more specific, this tidal decay assumes a fixed tidal quality factor Q at around 10 to the 7. Okay, but what are some other evidences? There are multiple evidences in terms of like what exactly is going on in terms of the dynamical events, how exactly you can get these USPs to that close regions, and what kinds of tides are operating. Because when it comes to tidal interaction, there's tides being raised on the planet by the star, and there's also tides being raised on the star by the planet. And they're both operating, and the tides being raised on the planet is especially relevant when there is a non-zero eccentricity. Sorry, there were other evidences, but given the interest of time, I cut them out. But I'm happy to discuss them during Q&A if there's an interest. All right, so something that is quite interesting is that if you take a look at the mutual inclinations of these USPs, they are systematically higher compared to the non-USPs. And I believe this is true even if you account for the transit probability effects. So that suggests that there's some sort of a dynamical upheaval or dynamical events going on, and maybe like we're going to hear more throughout this session of the different hypotheses. But at least like what's currently in the literature, one hypothesis that works quite well is this idea that the USPs, they are often in multiplanetary systems, and those outer neighboring planets can dynamically secularly scatter in the innermost planet. And if you just keep that scattering level to relatively low to moderate eccentricity, so something that's around 0.1 or less, then you can more gradually pull them in. And you also have to then like finally undergo the stellar tides, because eventually you're circularized, and now the tidal decay due to the tides being raised on the star dominates. There are other hypotheses using secular chaos to drive a pretty high eccentricity tidal migration, or even obliquity tides. But the problem is that they generally cause the USPs to arrive inside a day of orbital period really quickly. So around a few 100 million years or so. But if you take a look at the systematic, typical ages of these USP systems, they are particularly old. They're more like a few giga years. All right. Because I think this came up a few times during the discussion, I'd like to touch on this a bit. Is there any connection to the outer planets? So I've mentioned how there is probably some sort of a dynamical interaction between the USP progenitors and the outer planets. Back in 2017, something that quite caught my eye is this plot from Brad Hansen. And what you're seeing at is the distribution of the inner planets when you have an outer giant perturber. So either you have two eccentric perturbers, or one inclined perturber, or no perturber whatsoever. And basically, when you have an outer perturber, that allows for the sort of pushing in of the innermost planet to closer and closer orbital periods, which is interesting. And given sort of like what we have been discussing throughout, I believe, this meeting and also throughout the larger program, there are a couple of questions that we can ask. So can you form inner planets when you have an outer giant? And I'd say the short answer is yes. And the reason why the answer is yes is because, first of all, if you want to create the outer giant, you do require massive cores. So if that system has this outer giant, chances are you started with a pretty large mass reservoir within the system. But planet formation is a pretty inefficient process. So if you calculate what is the rate at which you can accrete and coagulate those solid bodies against the rate at which you can just drift all the material in by aerodynamic drag, it is about 10%. So that means you're losing quite a bit of material to the inner disk, interior to where you might be forming these giants. So that means during the formation of the large rock that might generate giant, you're losing much more material to the inner disk. And the second question you can ask is, well, let's say you were able to create these planets, and within the disk, it's going to create a gap, and therefore a bump, a pressure bump, and that can usually trap all this dust. So can planets just stop the dust flow with all these dust traps? And The answer is not quite, because these traps are quite leaky, and I believe that one of the seminal works were done by Zhaohuan Zhu, and also Paula Pinilla has done quite a bit of work on that. And in the simulations that we've done, what we find is that there is a difference between 2D and going to 3D. And if you go to three-dimensional simulations while keeping all the hydrodynamic properties of the disk the same, then we find even leakier dust traps when we do the three-dimensional simulations. And this is true even if you go to pretty high Stokes number. So we already knew that at low enough Stokes number, like we can leak quite a bit of a dust material, but that we see this leakage happening even for Stokes number around 0.1. Yeah, so I'm told to stop talking. So what I'm going to do is I'm just going to skip. All right, so I'm just gonna, given the interest in time, I'm just gonna stop over there. So there are other physics that you can use. We talked about tides, and there's also magnetic effects that I can talk about later. But just to bring everything together, starting from the radius gap. There is, you're gonna probably start with the radius gap from the formation, but keep in mind what that means is that there's a different regimes of this parameter space where you're probing different kinds of physics. So if you want to probe formation, you're going to have a much better chance at longer orbital periods. So especially if you find a lot of rocky planets beyond 50 to 100 days or so, they're likely born rocky objects. But the closer in you go, then you're probing all the physics of the star-planet interaction. So we've talked about the evaporation processes, so that's probably what's further sculpting the population of the rocky planets inside of about like 50 days or so. And like even further in, as you go down to the USP regions, the creation of those USPs are likely due to dynamical events, probably secular interaction by the outer neighbors, maybe the close neighbors, maybe even the outer giants, and also there is likely no problem, at least from the theoretical standpoint, there's no particular problem to creating the inner planets if you have the outer giants. Thank you.
Great. Yeah. Questions to Eve? Oh yeah.
Jack Lissauer, NASA Ames. Very nice talk. What aspect of the observed exoplanet population in the inner part do you find the most difficult to explain?
How inner?
Within 100 days.
Okay. Yeah, the farther and farther, well, like we just don't have data, unfortunately. I think, so something that, I think for the USP population in particular, not necessarily the edges, but like the overall occurrence rate and also their dynamical properties, and their ages. I think all of them together, it's a bit, I mean, like there's a way to explain it, but like it's not, I don't think there is quite yet like a solid physical explanation that just kind of gels everything together. Like especially the age and like all this like evidence of the dynamical upheaval. So I think there's like still a bit more room. And then also like what exactly is causing their sort of how far you can go in. Like is it the nearest neighbor or is it the far out neighbor? Like how exactly that number of planets and whatnot. Yeah, so I think that in particular is like something that would be good to do more work. Yeah, observation-wise, like I always like ask observers to say that can we get more mass measurements of the small objects? Yeah.
Hi, Emerson Tao, UC Santa Cruz. There was a slide that you had that was called, I think, the creation of USPs, and there was data from observed, I believe, stars. And I was wondering how you're able to derive planet periods from this data.
Right. So what you do is, well, let's see if I can do it with my hands. So it's quite simple. So this, for the stellar, what you're seeing here, that just gives you the inner edge. So that will just give you like how far in the planets can go, like absolute, sort of like absolute minimum distance that the planet can be with respect to the star. And you just draw that from a distribution because that is a distribution, right? And then for planets from there to farther out from the star, you just place them according to the dynamical stability, which is at least about like 14 mutual Heat radii that has been discussed in the literature.
Thank you. And sorry, just to clarify, what's the difference between the black points and the red points again?
Oh dear, oh yes, the red point is the one with the disks.
Gotcha.
Yeah.
Thank you.
Bennett Skinner, McMaster University. You listed evidence 3 and said you dropped evidence 1 and 2 for time. I'd be interested to hear what evidence 1 and 2 were.
Yeah. So this is evidence 1. So when you take a look at, so as I said, USPs are typically multiplanetary systems. So you can take a look at like how far apart these planets are compared to the adjacent planets. And it's a bit more widely spaced for the USPs, which is consistent with the tidal migration because it's an accelerating effect, given just how sensitive the tidal decay is with respect to the orbital distance. So that was evidence 1, and evidence 2 was the age. So I actually already mentioned this, but if you take a look at the typical ages of these USPs, and this age comes from the galactic kinematics, the kinematic measurements of the host stars, they are systematically older compared to the planets without the USPs, and also compared to the hot Jupiter sample, which actually also agrees with the tidal decay calculation. But exactly what kind of tidal effects, I think that's still a bit more work to do.
Yeah, I do have a question or like more of clarification. It's very interesting to hear you talk about the formation, evolution, that form the two populations of pure rocky and also as a gas atmosphere. Could you comment about the time scale, like of both of the process? Like, do we expect the formation to fully happen in all the systems? Do we expect the evolution, like the evaporation process, happen to all the systems?
Yeah. So formation would operate over this lifetime, basically. So 10 million years, maybe tens of million years now. Yeah. So that is when you still have a disk. Evaporation calculation, typically people quote 100 million years, but as I said, if you just look at the total cumulative masses that have been lost, it's actually pretty uniform across 100 million years, which means you're losing quite a bit after 100 million years, like up to giga years as well. Yeah, but that would only happen like if you have a high enough irradiation flux, right? Which means that you have to be close enough to the star.
As you know, the stellar dependence, then there are more observations we can do to test
it. So actually also a clarification question. So when you reconstructed the period distribution based on the observed periods in the clusters, I assume you used only the objects with the disks, right, to do that?
Yes.
Okay. Yeah. Because of course, when we look at many of the ones at upper SCO, they've already lost their disk and they're already contracting. Yep. So that case, those periods are probably not relevant.
Yep. Yeah, agree. Then, like, I did make sure to only use the ones with the disks.
Let's go with the last question.
Bennett Skinner, McMaster University again. When showing the photoevaporation curve in log-log space, it's a straight line, what you're drawing there. The My question is, whenever you're getting to like within a day, could there be any new effects that are appearing that would cause the kind of slope of that evaporation gap to possibly change so that the idea that what you're seeing is diverging from what you'd expect from just evaporation alone might no longer be true?
Yeah, that's a good question. So when we did, by the way, this looked like sketch, but it's an actual calculation. So in the actual calculation, we were pretty careful to not just assume certain, that the efficiency factor eta, because the reason why it's a complicated function is because there's a different, like what exactly is driving evaporation, the physics behind that changes. But even if you account for that, this will just go continuous, like straight up. Because like it's pretty much just probing, the closer in, higher irradiation, and you need more massive. Basically, it's much easier to transform like even more massive objects down to the rocky regime. So this will just continue to go up, which, by the way, is the reason why we had to. This motivated like why we. Oh, I'm sorry. Yeah, so this will just continue to go up, as I was trying to say, even if you account for all those different regimes of physics that is operating. Which is actually why it motivated us to consider the tides. And actually, I didn't have a chance to mention this, but accounting for the tides will allow us to explain why there appears to be a maximum 10 Earth mass limit to the rocky planets. If you did not have the tides, then you will not have that. You will just have a clear dependence of the maximum mass with respect to orbital period.
Thank you.
Great. Let's thank Steve again.